Good morning, dear student. In today's lecture, we will discuss the polymerization reactions of olefins. So, in previous lecture, we will discuss CC coupling reaction and some oxidation reactions of alkenes. So, in this lecture, as take the different notes from different references, so which is available, I will take this point. Therefore, before discussing the remaining point of oxidation, we discuss the polymerization reaction of olefins. So, polymerization of olefins, in which we discuss in today's lecture, that is the Ziegler-Natta polymerization of olefins. So, we are very much familiar with this Ziegler-Natta polymerization of olefins. No doubt, we discuss the homogeneous catalysis, but this Ziegler-Natta catalysis is an heterogeneous catalysis. But the importance of this heterogeneous catalysis, that is Ziegler-Natta catalysis in polymerization of olefins, is very important. Many times the question is asked on this polymerization, that is Ziegler-Natta polymerization of olefins, and therefore before discussing the homogeneous catalysis such as the use of metallocene for alkene polymerization, we discuss this is we already discussed in first year, so we again discuss this heterogeneous catalysis. You should remember this, and then we discuss the homogeneous catalysis, that is the use of metallocene in alkene polymerization. So before discussing homogeneous, we are studying heterogeneous catalysis. So what is this Ziegler-Natta polymerization? That is conversion of ethylene to polyethylene. So conversion of monomer ethylene into polymer, that is polyethylene. So the Ziegler-Natta catalyst, generally the mixture of titanium tetrachloride and triethyl aluminum is used, is considered as a Ziegler-Natta catalyst. The Ziegler-Natta catalyst is prepared by the treatment of titanium tetrachloride with triethyl aluminum in hydrocarbon solvent such as NH10. The Ziegler-Natta catalyst can cause the polymerization of ethylene and other alkenes under ambient condition, such as ambient conditions of temperature and pressure, such as at room temperature. So this Ziegler-Natta catalyst can be carried out. The polymerization reaction can be carried out at room temperature and atmospheric pressure, that is 1 atmospheric pressure, and therefore it is more advantageous over the old thermal polymerization of ethylene, and therefore it is very important. So the conversion of alkenes, carbon-carbon double bonds, into polyethylene in presence of Ziegler-Natta catalyst. So you should remember that is TiCl4 plus triethyl aluminum. Its mixture is considered as a Ziegler-Natta catalyst in presence of solvents such as NH10, and the temperature 25 degrees Celsius and the pressure is 1 atmosphere. So we are discussing the mechanism for this Ziegler-Natta catalysis. So if you consider in the first step, the titanium tetrachloride TiCl4, so it is a it having a coordination number 4, so 4 chlorine is attached to this metal atom titanium, and it has a vacant site. And therefore this triethyl aluminum, it will interact with your TiCl4, and there is a replacement of one chlorine atom by the ethyl group from triethyl aluminum. So what is happen in the first step? One of the chlorine atom which is coordinated to the titanium is replaced by the ethyl group from triethyl aluminum. So if we consider the first step, that is reaction with triethyl aluminum, the replacement of one of the chlorine atom by the ethyl group from the triethyl aluminum. So this is the first step. Then the titanium atom on the surface of the solid catalyst has a vacant coordination site. No doubt, there is a replacement of one chlorine atom by the ethyl group, but the titanium complex should have one vacant site, and therefore a molecule of ethylene is coordinated to titanium atom through this vacant coordination site. So in the second step, there is a vacant site, the complex contain vacant site, and the ethylene, it will binds to this vacant site, and there is a formation of TiCl3, one ethyl group is there, CH2CH3, and the alkene, that is carbon-carbon double bond, is also binds with this titanium. So if you consider the structure 3, in the first structure, the reaction with triethyl aluminum and replacement of one chlorine by ethyl group in structure 2, and then there is a reaction with alkenes. So we get structure 3, in which ethyl and the alkene is also attached to this titanium along with the chlorine atom. The next step of this polymerization is that the coordinated ethylene molecules is inserted into titanium carbon bond via 4 center transition state. So if you consider the insertion of this ethylene to this titanium carbon bond, so if you consider the coordinated ethylene molecule is inserted into this titanium carbon bond via 4 center transition state, and this process is known as cis insertion. So if you consider the structure 4, so there is a formation of 4 center transition state, and the coordinated ethylene molecule is inserted into this Ti carbon bond via 4 center transition state. Again, what happened in the next step? The ethylene molecule is inserted into this titanium carbon bond, and due to this insertion, again there is a generation of vacant site. So what you get after insertion? We get this titanium, which is attached to 3 chlorine atom, and we get here CS2 and ET means CS2CH3. So the insertion of this ethylene to this titanium carbon bond, it is the important step. So it is a 4 center transition state, which is also known as cis insertion. The result of cis insertion is that the vacant coordination site is regenerated on the titanium atom, and it is again occupied by the second molecules of ethylene, and the processes continue to get the processes continue several times. The resulting substance which is obtained, such as polyethylene, is a straight chain polymer. So the polyethylene which is produced by free radical process has a branch structure. So what is the advantages? We get a straight chain polymer with the help of this Ziegler-Natta catalyst. The straight chain molecules fit together, and hence straight chain polymers have high melting point, and it will form strong fibers. Again, such polymers are said to have a high degree of crystallinity. On other hand, the branch chain polymers are non-crystalline and having a weak mechanical properties. So these are the advantages of this Ziegler-Natta catalyst. The mechanism was proposed by Cozy and Earlman, and hence it is called as Cozy and Earlman mechanism. And the last step, that is the chain termination. So no doubt, so these all other steps, that is the coordination of ethylenes to give polyethylene, it is the propagation step. And the chain termination can be takes place due to the beta hydride elimination or hydrogenation reaction. So if you consider the first, that is beta hydride elimination. So with respect to this titanium, this is your alpha carbon, this is your beta carbon. So CS2 CS2R. So CS2, it is your alpha, again second CS2 is your beta carbon, and there is a beta hydrogen. So beta hydride elimination is there. So hydrogen is transferred from this carbon to this titanium. So we get TiCl3 and H plus a removal of CS2 double bond CHR. This is the termination by using beta hydride elimination. And the second, that is the hydrogenation reaction. That is TiCl3 CS2 CS2R react with H2, and there is a hydrogenation. We get TiCl3 and one hydrogen is there, and we get RCS2 CS3. So this is all about the Ziegler-Natta catalyst. In next lecture we will discuss about the homogeneous catalyst, means the metallocene is used as a catalyst for this polymerization reactions of alkenes. Thank you.